Hello, we are Team 5. Last week, we talked about the floor plan of Abbey Park. The office building has an outside diameter of 1.532 feet with a ring width of 180 feet. 8 of the edges are for office, lab space, and one of the edges is the restaurant in town square. There are 9 entry structures where each of the edges meet with a full 8 atria that create light-filled common areas to provide social space that connect the office park to the garden space within. There are 9 elevators and stairs in the part of the entry structures which are the core system of Abbey Park. Continuous hallways are located adjacent to the glass at the inner and outer perimeters, with the outer hallway being nearly a mile long. Also, we handled the void slab and girder. So today, we're going to talk about the PC method, which is used in Abbey Park, and the cross-section in detail, including column, girder, void slab, and access floor in turn. Abbey Park is thought to be the largest precast concrete building ever built. PC, abbreviation of precast concrete, means the concrete members that make up walls, floors, and more are made in a factory in shapes and sizes that can be transported ahead of time. In other words, it is prefabricated in a factory and only assembled on site. The on-site construction sequence of PC method is as follows. First, since PC is a method of connecting one separate mass, a hole must be drilled in the foundation floor at the correct location and at the correct depth, so 4 anchors are installed in the place of the column anchor. Next, the 4 holes at the bottom of the columns are installed to fit the anchors. At this point, a crane is used to lift the PC column and install it. After the columns are installed, the factory fabricated members will be installed, followed by the PC girders and PC slabs, and finally, the topping concrete will be poured to integrate the field assembled members. This is our 3D modeling, which simulates the part of the construction of Abbey Park. Now, we're going to introduce about the main structural members in Abbey Park. First, it's a column. For columns, molds are made and prefabricated rubber and embedments are installed. Next, the concrete is poured, steam cured, and the mold is demolded once curing is complete. Next, we'll move on to the girder. The girder and wall ledges were designed for the concreted reaction. In Abbey Park, the inverted T girders were used to achieve efficient load distribution, ease of installation, and reduced structural height. Also, the post-tension beam construction method was used. Due to post-tensioning, it can adapt seamlessly to complex and large-scale structures directly on site and can apply greater tension, supporting larger loads and extending the spans of structure. These girders repeated themselves at every interior radial grid line. The girders also had to perform as collector elements, delivering more than 500 kips of force to the shear walls. The surface space below the girder was shrouded with either an architectural beam cover or partition framing where walls were placed. Next, we move on to the void slab. The void slabs rest on ledges of precast post-tension girders, or on a continuous ledge at the shear wall lines. The support connection chosen was a trussed hanger bar, a rectangular steel bar with welded inclined rubbers that transferred the reaction into the stems of the unit. The internal structure of this slab is as follows. The method deck connecting the upper part of the precast is raised, and as the space underneath is hollowed out, a hollow layer is naturally created, and a concrete diaphragm is poured on top of the metal deck. Compared to regular slab, the void slab has a lighter weight. Also, the shape of the slab itself automatically creates a beam shape due to the space between the slabs, so there is no need to install additional beams. In addition, the existing space for beams is eliminated, so it can maximize the utilization of space, which further achieves the openness of the space that Steve Jobs wanted. Next, we'll move on to the access floor.
The following figure shows the overall cross-sectional shape of the ceiling. The full slab model would be the bottom part, and the empty space above is the access floor. With mechanical, electrical, plumbing, and network services all slated for the 18-inch access floor space and the ceilings thought to be inaccessible due to the solid ceiling slab, space became very tight for those services. The first step in solving the mechanical problem was to reduce the forced air duct requirements by utilizing the thermal mass of the concrete and providing a radiant cooling system in the ceiling. This was achieved by placing coiled loops of chilled water PEX tubing into the soffits and daylighting them in manifolds that would be accessible in the above-the-floor slab. The tubing was set up in circuits that coordinated with different climate control zones. The chilled water radiant ceilings dramatically reduced the HVAC demands, but space was still limited. Next, to utilize the void space in the ceilings as a return air plenum, the void slabs needed to have perforated stems so air could move radially through the soffit space to return air registers. The void slab units were updated with stem penetrations in the idle section of the span. In addition to mechanical coordination, the perimeter void slabs were highly coordinated with other trades. To facilitate construction and promote prefabrication, not only the embeds for the brackets were installed off-site, but also the brackets themselves. The plumbing for the mist sprinkler system was pre-installed in these units as well. And lastly, the perimeter metal edge deck form and temporary handrail were also pre-installed off-site. Prefabricating these activities off-site dramatically reduced on-site labor and equipment. Over 4,000 of these highly complicated void slabs were constructed to make up the signature interior feature of this iconic building. Another 10,000 pieces of structural precast elements comprised the frame of the building. This monumental building project redefined how multiple phases of design and construction can occur and interact. Through the cross-disciplinary design and the motivation to pre-manufacture complicated elements and systems off-site, the complete integration of architecture, structure, and mechanical services in building elements was realized. Thank you for listening.